right, well, good morning or good afternoon, everyone. It's about that time, so let's go ahead and get started. Welcome to today's webinar, again, where we'll be going over some key facts that you need to know about Markforged composite and metal 3D printing. So again, my name is Jesse Hallworth, and I'm a 3D printing application engineer at Hawkridge Systems. And with me is Patrick Olson, who is the Federal Account Manager for Hawkridge. So as a quick overview for today's session, the first point we'll cover is who is Hawkridge Systems. Once we go through that, we'll go right into the Markforged 3D printing technology and hopefully help to answer the questions of why you might choose to use their solutions. This is going to include an overview of how they print composites and what applications we see being printed with these systems. And after that section, we'll be doing something similar with the Markforged Metal X 3D printing process. And you can actually see two of their metal printers here on the right of this slide. And for the very last section, we've put together a section that outlines 4 specific customers that are using Markforged printers to accomplish tasks in a better or more efficient way than what they were doing before. This one was tough because there is a lot of companies using Markforged printers for some really cool things, but I think what we'll show here highlights a lot of the benefits of these particular systems. So getting started here, like I mentioned, I first want to go over who Hawkridge Systems is and what we do. So Hawkridge as a company has a goal of, in really basic terms, of helping you find the solution to your problem. We have a ton of different products that we provide and also support, and that ranges from CAD design like SolidWorks to things like data management, simulation, CamWorks, and that goes all the way through to physically prototyping and producing the parts that you're designing. So rather than focusing on one specific thing, we want to make sure that we help you find whatever your pain points are and if we can help you with those. So Hawkridge has been around since 1996 and started with SolidWorks, and since then has basically expanded as a company, but also with the customer base. So right now we have almost 300 employees spread out over North America in multiple offices. And so, like I mentioned, we have a lot of different partners that we work with, and here's just a quick overview of the major ones. You can see things that this covers basically the whole process of design, manage, simulating, and manufacturing, and we even have partners for post-processing your parts if that's something that's interesting to you. And we have this slide here to show some of our current customers that we currently provide support for, both Markforged and other products. And like I was talking about, we have a lot of different locations, but in terms of Markforged, we actually cover all 50 states. So if you ever have any questions or need help, there's always going to be someone in your time zone to work with you. And so moving on to Markforged as a company, they've been around since 2013, and they were essentially founded on the question of what if we could make a printer that creates parts strong enough to actually be end use. So their headquarters are still in Boston, where they were founded, and even though they do have a global presence, all of their hardware, materials, and software are both designed and manufactured in the United States. They also operate through a partner support model, which, as you can probably guess from our last slides, means that they have partners like Hawkridge sell and provide support and training for their equipment. Now you'll notice that I mentioned materials and software instead of just hardware, and that's because Markforged focuses on more than just building printers. They build their own print preparation software, which is called Eiger, and a bit later on today, I'll be going through what's involved in actually setting up a part in that software. Their software is also the only 3D printing software that has ISO 27001 certification, which basically means that it meets some really high privacy and security standards. Markforged also has an entire team dedicated to creating new materials. And because they develop stuff within their ecosystem, you're able to get up and running with different materials without having to change stuff like feed rates or temperature profiles in the printer itself, because Markforged has already done that legwork for you. And so speaking of materials, let's start out with an overview of the Markforged composite printing process, because that is what Markforged started with. A Markforged composite part is mainly printed with a primary plastic matrix, which there are a few of, but by far the most used material is onyx, which is a nylon 6/6 material that's made with chopped carbon fiber, which gives it a really nice black surface finish. And so because it's mixed with these chopped fibers, you already get some much higher and better properties compared to stuff like ABS or even nylon printing materials. Now that's all well and good, but where the real fun starts is with the internal continuous fiber reinforcement that can be done with Markforged systems. So as you can kind of see here with this representation, Markforged printers will lay continuous strands of fiber inside the main body of a part, and these fibers are how Markforged achieves some really strong composite parts. A lot of the times you'll hear other materials being advertised as printing with carbon fiber, but most of the time these are referencing materials that are mixed with chopped or short strand fibers, and these aren't really the same at all in terms of benefits. And so speaking of those continuous fibers, Markforged has 4 primary ones, and the most well-known being carbon fiber, but they also have stuff like different types of fiberglass, high strength, high temperature fiberglass, so those really high temperature applications, and then a really cool one, which is Kevlar, which really helps with abrasion and impact resistance of parts. And again, that's all well and good, but what does that actually mean in terms of benefits? So you'll remember that I talked about onyx being the most popular plastic material that Markforged has. And if you look at the stress strain curve here on the left, you can see that it does have some higher values than something like ABS, which is a really popular 3D printing material. There are also other types of onyx like ESD, which stands for electrostatic discharge, that you can see on the left-hand side graph as well. But if we move over to the right-hand side graph, which shows the 4 different types of fibers that I just mentioned, you can see that we really start to get into just an entirely different league here. Just as a comparison, you can see that the onyx is still located there on the bottom right. But one other thing you might notice is in the top of this area, which shows continuous fibers compared to aluminum 6061. This is always a really good graph to look at because it really shows how you can get parts that have a higher strength to weight ratio than aluminum from just a 3D printer. I've always thought that's really, really impressive. Okay, so we've described the composite printing process and gone over some numbers, but what I like to do is show an actual example of the strength of fiber reinforcement. So what we have here is a chain link just undergoing a test, and they basically wanted to take this fiber reinforced chain link to the limit here. So it's just under 22,000 pounds. It gets to that amount, and it breaks right as it crosses that mark. So having a 3D printed part that can hold 22,000 pounds by itself is nuts. And you're probably not going to be printing all your chain links on printers from now on, but it just goes to show as an example of what can be done. So I wanted to show an additional example, but this one is a bit more real world. So here you have the company CLAAS, who makes equipment like harvesters. And so they took the chain link concept from the previous slide and decided to apply it to the application of moving their equipment around facilities. So we can see that they're weighing the vehicle, which is a bit over 17 tons. And as you can kind of see, they're utilizing 4 different links to set this up. And remember, these are primarily made out of a plastic base. So they're going to be a lot lighter, easier to handle, easier to move around than a metal equivalent. And so once they get those connected, they're able to lift the vehicle up and move it around no problem. So I think, again, that's just a really cool example of being able to move something that heavy around with just a 3D printed part. And here's the example of them just transferring that to a different location here. So if we move on a bit from the material side to the actual machines themselves, we'll start with the desktop series of Markforged printers. I have a bit of stats here on the right, including the build volume and printer footprint, and you can see that these particular printers don't take up much space at all. There's 3 different machines here, which are the Onyx 1, the Onyx Pro, and the Mark II. And you can see they all have different capabilities for what fibers they can inlay. If you have a really wide range of applications, for example, like something that really needs the stiffness of carbon fiber, then the Mark II on the top there is a really great intro point to these machines. And so just to give some context, those chain links that we went over in both of those previous examples were actually printed on these desktop machines. And I think that's a great example of the capabilities of these systems, 3D printing up a part that can support 11 tons by itself on a machine that fits just on your desktop, but that's pretty intense. And then here we have a few stats on the other line of Markforged composite machines, which is called the industrial series. So these are bigger systems with a bigger build volume as well, which makes it a lot easier to place more parts in a build. And that makes it so you have better control of your uptime, because if a machine like this is going to be running without any input from a user anyway, then having a job run fully overnight and in exactly when you want it to the next day is going to help you get the most parts out of it. So these systems also have a laser micrometer built into the print heads, and that helps scan the print bed automatically before each print for build flatness and make sure that your build is level as well. This is another automated process, and if the bed needs to be releveled, then the same laser will help you get releveled in a few minutes. So there's really not a lot of user input on the hardware side to get it up and running other than loading material. And the XY accuracy figure here on the bottom is plus or minus 125 microns, which is very slightly under 5 thou. So these are really accurate machines in the plane parallel to the print bed. And then in the Z direction, the accuracy is typically plus or minus the height of one layer. So there's a few different layer heights that can be selected. And because of the accuracy of these machines, they can print down to 50 micron layer heights, which if surface finish is important, that usually results in some really, really nice looking parts. So a big part of the design philosophy behind both of these composite lines is to keep them simple, because a lot of times more moving parts can essentially just mean more points of failure. So some really big positives with these systems is that they don't need any heated chambers because nylon is already a really stable material. And speaking of the material itself, it's stored in a dry box with no mechanics. So there's only one extrusion motor that moves material. And the print bed itself is one solid piece that can be removed easily. So there's no moving or electronic parts on that side either. So that simplicity lets Markforged create stuff like the X7 Field Edition, which there's a picture of here on the right. So what this is an X7 system packed into a big Pelican case with space for all the tools, materials, and service parts that it might need. So this is meant to be carried around to a remote location where there could be a lot of supply chain related problems if you need something like a replacement part or a custom tool. And that's a big strength of 3D printing in general, which is solving supply chain issues. This is currently being used by the Marines, and essentially all you need is to remove it from the Pelican case, which also acts as a table, plug it in, get material loaded, and you're ready to print. And all of that usually takes about 3 to 4 minutes to do. Okay, so we've gone over the composite materials and the printers as well. So what about the software? Well, like I mentioned earlier, I'm going to bring up Eiger here and go over exactly what it would take to set up a file for printing on the Markforged system. So here I have a part already brought into Eiger. This is an STL of a composite gripper jaw that goes on the end of a robotic arm. And like I mentioned, it does accept STLs. So Eiger is really CAD agnostic. So no matter what CAD software you're using, it's going to export STLs. So you're going to be able to bring your parts into Eiger here. The actual movement and setting up a part in Eiger is very, very simple. So right now I'm just holding the mouse button to get a better view of my part. Zooming in with the mouse wheel, not a lot of complex controls here. Now, usually a part will be brought in on its flattest surface, but let's say if I wanted to change its orientation, I have a couple ways of doing that. If I mouse over some of the surfaces of my part here, you can see that they're highlighting blue. If I click on one of the blue faces, it will align that surface to the print bed. If it can't align it to the print bed, so something, a feature is keeping it from being directly on the print head, you can see that it's going to place it parallel to the print bed and not cut off any of your geometry or leave you with any partial prints or anything like that. So that's a really easy way to orient your parts, just get them flat on the print bed there. If you see over here on the right, we do have a couple different options as far as material and orientation. So Eiger manages all of the Markforged printers and software as well, and materials. So let's say you have both different types of printers, a composite and a metal printer, and you have a part that you want to print in a different material. You can just select that from this list and slice it, and it'll be ready to print on that different printer. Reinforcement material, we'll leave this as onyx because we're still going over a little bit of composite stuff. I can pop this down if I want to enable carbon fiber. Really easy just to do that. And then here's a few other manual controls here as well that I can use if I want to. There's a few different settings here as well that you can use. So there's a couple different things that you can change. You can change the scale of your part. You can set it to use supports or not if you don't want to print any overhanging features with supports. If you know that it'll print, you can do that. And there's a couple other different options here as well, but I won't necessarily go over every single option available. There are some different infill options here as well. So if you can see here, if I select this drop down for fill pattern, the default is triangular, but if you wanted something like a solid part, say you want to bore holes into it, you can do that pretty easily just by selecting that option. But I'll leave it as triangular fill for now. And because we have some fiber enabled, if I go to the reinforcement tab here as well, we have different options. We have total fiber layers. We can change this. And by default, what the Markforged software will do is split whatever number you have here in half and place half of that number near the bottom of your part and half near the top. Gives it a little bit of a sandwich panel configuration. You can change the fill type, but there's different fill types here as well. And then there's a couple other different options that you can change as far as the amount of fiber in those particular layers that you have set. If anyone here is a hobbyist as far as 3D printing goes, you'll notice that there's a lack of the really in-depth options as far as stuff like I mentioned earlier, like feed rates, temperature control settings, and all that kind of stuff. And those aren't necessarily bad things, but these are meant to be machines that you use at work. So if you're doing something important, you don't necessarily have time to set up different in-depth options for your 3D printing machine. You just want to be able to get it up and running and get a part on the bed really quickly. So that's what you're able to do with this machine, because Markforged, like I said, does that legwork for you. So we spent a minute or two here just going over these different options, but if we hadn't done that and we just wanted to set up a part quickly, we would just bring it in, click save, and then the software is going to slice that for us, which means it's going to toolpath every individual layer that the printer is going to be printing while this job is printing. And so like you saw there, that wasn't a very long process at all. So because this part is sliced and toolpath, it would technically be ready to print at the moment. But I do want to show one additional thing here, and that's going to be the internal view options that you have once a part is sliced. And what the internal view lets you do is do a couple things with fiber, also lets you see each individual layer and a couple other different things here. So same controls as I'm in the internal view here. And if I change the view option to 2D, what you can see is I can scroll through each individual layer. Not a lot of these layers are going to look different because the part's pretty symmetrical all the way through. But if I get to a layer with fiber here, you can see an example of the infill and then the blue fiber pathing, which is going to be where the carbon fiber continuous strands are going to be inlaid around the part. And you can see that they're kind of supporting the entire wall of the part here. Now, let's say, for example, I have a feature somewhere in the middle of my part or somewhere that wasn't reinforced because of those default settings that we had. Let's say I want to reinforce this particular hole for whatever reason. So what I can do is I can select just these layers of fiber here and just toggle Eiger to use fiber. Let's say I don't want to actually reinforce the entire layers that I have selected. I want to do some stripes. So what I can do is I can change the fiber pattern type to stripes here, and then just mess with these options here. Get kind of the feel that I want. You can see that once I have these options that I selected, it's sliced in real time. The cost metrics are updated, and you can see the representation of that fiber group there. Let's say I didn't want that. What I can do is I can revert, and that will take us back to the last saved state of that part. So again, like I said, these are really simple options here. You don't really need to have your high-skilled labor do this necessarily, because this is going to be something that anyone can really do and set up and manage. And I did want to show this particular part here, just as another customer example, because this is something that Dixon Valve used for an example of one of their end-to-arm robot effectors. So what they did was that originally they machined these parts out of aluminum, and one of these parts cost about $300 to machine. And they used a setup similar to what we have right now in the software to get it down to about $10 per part. So it isn't necessarily something they needed to machine out of aluminum, and they were able to get a lot of cost savings on just one small little part here. Everything that we've kind of been talking about together on the composite side, I wanted to continue to go over some general application areas that these printers and materials are used with. So the first one we'll cover is work holdings. So this is items such as soft jaws, welding fixtures, things of that nature. Stuff like this can be a pretty big machining pain point because you have to machine an item just to hold the actual item that you wanted to machine in place. So when it comes to soft jaws especially, we see a lot of this particular application because the biggest things you need your soft jaws to do is obviously hold your part in place without deflecting, be resistant to wear, and also be resistant to potential chemicals or heat. So the Markforged systems can produce parts that meet these requirements. And as you saw from the software demo that we just did, you don't even need to have your machinists set these up because they can spend time working on more important tasks. Another area we see a lot of is tooling. So stuff, again, like end effectors, punches and dies, and even molds, like on the lower right. So there's multiple Markforged parts on the lean machine example on the left, with the robotic grippers moving parts into Markforged printed bending die. The fiber reinforcement on that end gives it the stiffness needed to perform jobs like that. And if weight is a big concern, like it is with stuff like end effectors or again jaws on robotic arms, then the sparse infill parts can be a really big plus here, because the lighter those parts are, the more operations that the actual machine can perform. And then as a final category, we have parts that can help with the quality control process, though this can really be any sort of gauge or, again, sort of fixture part. So the biggest example I wanted to bring up here was from Dayco, who printed some profile gauges pictured on the left to help align automotive parts and assemblies. So they machined these out of aluminum originally, and that took about 200 hours to do for a set. They completed the Markforged version, and that was almost 60% less cost in materials. And they were also able to finish that in about half the time. But again, like we've gone over in a few slides back, those are unmonitored hours and not necessarily man hours. So that lets their staff focus on other things, which can in turn impact the turnaround time on other projects. Okay, so we've talked a lot about the composite side of things, and now we're going to move on to the next section here, where we'll cover the Markforged Metal X. Now, the question is, if the composite parts are so strong, why would a metal 3D printer be any use? Well, the obvious answer is that some parts just need to be made out of metal, right? It could be the environmental factors, or it could be the surface your part will interface with, but some jobs just need a metal part. And so looking at the stats for the actual printer itself, you may see that it's fairly similar to the dimensions and accuracy of the industrial series machines, especially in the important parts, like part accuracy, which again, plus or minus 125 microns here. Now, before we move too deeply into the rest of the metal section, I wanted to briefly go over what's involved in printing a fully metal part. So Markforged uses a process called atomic diffusion additive manufacturing, which is just ATOM for short. So the first step is, after you design your part, you print it using a material spool that's made up of metal powder that's bound up in wax and polymer. So you don't have to worry about using a bunch of intense safety gear to avoid loose metal powder, because it's contained in spool form by that wax and polymer. And so then once you have that part, it's known as a green part. You wash it in an industrial degreaser to get some of the wax out of it. And so once that's done, it's called a brown state part. And all that's left to do after that is sinter it, and you have your end use part when that's done. So once you sinter it, the part's fully metal and it's ready to use, though you can post-process it in any way that you want after the fact. Now, if any of those last steps sounded familiar, that's because when they were working on their printing system, Markforged based the whole thing off of metal injection molding, which has really been around for quite a few years now. So in comparison, metal injection molding typically uses a feedstock, a washing system to remove the binder of that feedstock, and a sintering solution as well. But that system is really used for production of thousands of parts, and it doesn't really scale downward that well. So what Markforged did is take that idea and just scale it to a smaller level, so that it doesn't have to be used for thousands of parts, because there are already a lot of production methods that exist to meet that level of output, and they may not necessarily need what you're trying to accomplish. So just to visually go over each of the steps we talked about, we'll start with the printing process. So like I was talking about on the last slide, the actual printing is the same as on the composite systems. So parts are printed layer by layer until they're done. Because it's the same, we see a lot of users with composite experience move over to the metal side of things really easily, and they're able to use some of the same design practices that they do on the plastic side. And so as you can kind of see with this sped up example clip, parts are still printed with sparse infill by default, which would quite literally be impossible to machine. So because a sparse part isn't going to be as heavy as a solid one, this lets users take some really unique approaches to their parts. So just as an example, if an application typically uses aluminum for the weight properties, but it still needs to be metal, maybe print a stainless or tool steel equivalent with a sparse infill to get that same weight reduction. So that way you get the properties like higher hardness of a different metal, but still save weight versus a machined version. And speaking of steel types, Markforged currently has 6 different types of material available, which are shown here. Inconel, 625, and copper are the most recent, but you can see that there's several different types of tool steel to meet specific applications as well. 174 is also on there. So there's a lot of different options. And one of the really huge benefits to the way that Markforged sets up their whole method of metal printing is that, as you can sort of see with these pictures, all of the materials are still spool based and are made of, again, that metal powder bound up in wax and polymer that I mentioned. And so these are all usable on a single machine as well, since the material is still spool fed. So if you're printing something like a stainless steel part and next want to print an Inconel part, for example, all you need to do is unload the steel and then load that spool of Inconel. So there's no hardware swaps needed or anything like that. This gets really cool for stuff like copper, which is really hard to machine traditionally and requires some really, really specific hardware on some larger powder-based metal 3D printing systems. Okay, so once you have your green part printed, next, like I mentioned, would come the wash, because some of the wax does need to be removed from the part before it's sintered. This is done by washing the part in Opteon SF79, which is an industrial degreaser. Eiger tells you how long you need to wash your specific part for, and parts aren't going to dissolve or anything like that if you leave them in there too long. So you can leave them in there, say, for a weekend if you forget to take them out on Friday, and they wouldn't be affected at all, either pre or post sintering. And finally comes the really fun part, which is the sintering and actually getting the metal part in your hand, right? So during the sintering process, all the polymer that's left in the part is burned away, and the remaining metal in the part will fuse together to a near net shaped part. Because the sintering unit does this fusion of particles, the parts you get are going to be isotropic. And once you get the part out of the sinter, it's immediately ready to use, though you can post-process it, harden it, or even machine it if you really needed to. And here's just a quick shot of pulling some parts out of a Markforged Sinter 2 sintering unit. Another really cool thing about these machines is that, as you can kind of see from this particular picture, there's quite a few being parts taken out, and the sintering for this amount of parts would be the same amount of time as if only, for example, one part were in the unit. So if you're working on a big project with a decent amount of parts that you want to complete all at once, rather than being staggered, the time cost is not going to increase for that. Now, I would say that one of the most common questions I get is, how does this actually compare to something I could get from a machine shop, or maybe even from our own internal CNC? So for this slide, we're going to go over that bit using the 17.4 stainless steel material as an example. So on the left here, we've got a stress strain curve for a metal injection molded, a wrought, and a Markforged version of the same test pieces. And as you can see, even though Markforged is based around the idea of metal injection molding, they were able to improve upon the actual results from the process when creating the Metal X and the atom printing process. So there's quite a few figures on the right that tell the same story, that basically you're getting really close to the performance of a machined part from a Markforged equivalent. I'm not going to go through all the different metals or numbers here, since the results are all fairly similar to what you can kind of see, but I do want to point out one more example with stainless, and that's going to be the density of these parts. So you can see here in the upper right that there's a microscopic view of, again, same metal injection molded, machined, and a Markforged part that are all heat treated. So the metal injection molded one is in the center with Markforged on the left and the wrought part on the right. So at this level, you can really clearly tell there's a difference between the metal injection molded part and the other two. And again, that's kind of just to point out that these are real metal parts and they are going to perform like it too. So numbers are great, and I love showing stuff like that, but I also like showing where these are being used and what types of applications you might use this solution for. So this first slide we have here are all examples of functional prototypes. So since you're printing in metal, you can print stuff, you can put stuff through its paces like real parts, but printing stuff in-house and having it in your hands within days rather than weeks lets you make design changes and test them on much shorter timetables. So as an example of that is the diesel fuel injector from Sandia National Labs in the upper right, which previously what they were doing is having this being created from third-party laser sintering machines with powder-based machines, and then they had to CNC it internally to create some of the internal cavities that they needed. So they really didn't need a ton of these parts at a time. And because the volume was really low, sometimes it would take them weeks or even months to get a single part just to implement a design change. So after they brought the Metal X in-house, they're able to easily print the part on their own and then process it with their own internal equipment, which kind of like I've been mentioning, shortens that timetable on their projects. And so the next category of applications is a pretty big one, but this is going to be general tooling. This will be stuff like punches, dies, presses, or even welding shanks like the printed copper one there in the upper left. If you remember at the start of the metal section, I was mentioning how some parts just need to be made out of metal. And a good example of that is, again, Dixon valve gripper jaws on the side. So as you can kind of tell, Dixon valve has a lot of Markforged applications, but for these particular jaws, they interface with some really sharp threads. And so that doesn't really work well for plastic. So they print these particular ones out of metal, and because they still have that sparse infill, they're able to save time on getting these created while also saving some weight on the machine. And then lastly, we have just general end use parts, and these can be either for production or a quick replacement part. And that particular use means that you don't have to keep physical inventory because you can just print one and have it ready to use in a few days. A really interesting highlight here is going to be the PTZ tool cooler on the upper right. And so this part was originally made out of aluminum, and what it's supposed to do is disengage a cutting tool. And so the more conductive and efficient the cooler is, the faster that they can reconfigure their tool. So their original aluminum version wasn't really meeting their expectations. So they turned to Markforged for a potential copper solution. And so this version that they ended up going with also has some internal cooling channels, which again would be impossible to machine, but that they're able to create with the Markforged printing process. So with the copper version, PTZ is able to cycle much quicker than they were originally able to. Okay, so we've gone over both the metal and composite solutions from Markforged, and that will bring us to our final section of the day, where I want to go over 4 specific customers and how they're using Markforged systems to accomplish something in a better or more efficient way in comparison to what they were doing before. So the first customer highlight we'll cover in this section is going to be Team CoStar, which is actually a collab between multiple organizations, some of them being the NASA Jet Propulsion Lab, MIT, Caltech, and the Korea Advanced Institute of Science and Technology. So CoStar is taking place in the DARPA Challenge, which basically has teams working on an automated solution to explore caves and caverns to mimic the conditions that something like this might experience on another planet, or maybe even some rough terrain on Earth. So the big challenge for the team here was to have a solution for parts on their robots that were not only lightweight and resistant to impacts, but could also be quickly replaced or changed in some way if they broke. So they tried a few different things like wood and machine parts at first, but out in the field, that's not really going to be a viable option unless you take a lot of them with you. So they did explore 3D printing, and right at the beginning, they bought a small little PLA printer And that met two of those conditions that I brought up earlier. But they were finding that the surface quality was really poor, and the parts weren't accurate enough. So they were spending too much time post-processing those parts just to make them usable on their machine. And even after that, they just weren't strong enough to protect the really expensive components on the robot, like the LiDAR sensor up on the top of their bot here. And so in the end, they ended up working with a Markforged printer to print onyx and carbon fiber reinforced parts. And the main assembly they use is a cage to protect that LiDAR sensor that I was talking about. And you can also see it highlighted in yellow here in a smaller picture. So this gave them a solution to all three of their problems, and their team brings multiple printers with them now on trips so that they can design or change parts in the evening, print them overnight, and then test them the next day in the field. And so for our next highlight here, we're going to cover Wärtsilä, and the location that's covered here actually oversees the building of cargo ship engines for a really large portion of the world. So specifically, we'll cover a lifting tool that they use to, well, lift heavy things like pistons. So obviously, a big thing with something like this is that a good tool can make the manufacturing process of something like a big engine much more efficient. So at first, they were usually having the tools here machined out of solid steel. But some of the big challenges we've been talking about today were present here too, with the steel version being too expensive, taking too much time. And another just really big point was that they just were too heavy for people using them to lift around and move easily. So this one is huge because if the tool takes too long to set up for maintenance on a component, then your efficiency drops. So the unique thing about this case is that Wärtsilä actually already had a few Markforged printers and wanted to use this as a solution. So they ended up buying the larger build area X7 to split the tool into multiple pieces and test different designs of each piece fast. So in the end, they came up with a design that could lift 960 kilograms of weight, which means it was able to actually get internationally certified to lift 240 kilograms, while also saving them about 100,000 euros in just this tool, all at the same time being 75% less heavy than the previous solid steel version. So being able to do stuff like this with a 3D printed assembly is really letting them become more independent of supply chains on their side. And so moving on to our third story here, we're going to cover a metal application that was used by RPG Industries, who is a manufacturer that works in the automotive, aerospace, and oil industries. This story is a spotlight on a carburetor, which you can actually see a test version printed out of onyx there in the background of this particular picture. And so for this case, RPG Industries was working with a customer by the name of D&D Classic Automotive Restoration. So the customer was working on a 1930s classic car, and while they were doing so, they found that one of the original carburetors was broken, and they couldn't repair it by welding it or anything else because they needed an airtight and watertight seal. So they tried finding replacement parts, but they didn't exist because the company that originally made those were long since gone, since again, this is a 1930s car. Okay, so that means they would actually need to make a new one. They looked into machining, but all of the channels and features needed to match the original piece, made it almost impossible to machine, and just in general, too expensive to do so. So the president of RPG Industries had been thinking about bringing in metal 3D printing for a while, but he only knew about the powder-based solutions, which cost a ton and also have a lot of safety concerns with those loose metal powder as a base material. So while he was looking into that, he eventually found the Metal X, which fit his price point and was also much safer because it doesn't need any dedicated safety equipment. So what they ended up doing was bringing a Metal X and a composite system in-house, scanning the original carburetor, printing that test piece out of onyx that I mentioned earlier, just to make sure everything fit right, and then printed the final metal piece for the customer, who then used that piece to fully restore the car. And you can see the final version there highlighted in that smaller picture. So this may seem like another supply chain example, and it is, but in the sense that the supply chain for this part just didn't exist. There were no suppliers here, so you either need to get the part built or bring in methods to do so yourself in-house. And so even if a part is available from a supplier, if it takes you weeks or months to get it, then you could be dead in the water on a project in the exact same way. So Markforged is really useful in cases like this. And then for our last customer case here, I figured I'd give everyone a bit of a break from listening to my voice and play this video of our last customer example, Siemens, who has multiple applications to show here.
The Innovation Center, we're an end-to-end solution provider within Siemens. We're able to take a concept all the way to final implementation, all under one roof. So we saw the capabilities of the Markforged printers, and we saw the finished quality we get from the prints, the strength of the material, and we wanted to have a more industrial printer to be able to fast prototype and also potentially using it as a final tooling. When we first used the Markforged printers, a lot of people thought it would just be used for prototypes. And so there was an initial surprise by our end users that we were actually giving them a 3D printed part that they could actually use in the field or in a repair facility or manufacturing facility as the actual tool.
The major benefit of having the 3D printers in-house is that the time to develop an idea is dramatically shorter. Within a day or 2 days, we can go from an idea that we whiteboarded to a CAD model to a 3D printed part in our hands. So it drives the cycle time down as well.
The Markforged industrial printers act as a digital factory for us. In the past, you would have to make design decisions, do down selections during the design phase. We can now take 3 or 4 different designs, print them out, do the form function test, and then make a decision there which way to go forward. It just allows us to cut costs, and that money is realized back within the business units.
So with the Markforged 3D printer, we get great resolution on the parts. It looks like a real tool that you would buy from a store or something that would be in production.
So if there's an issue with one of the gas turbines out in the field and it has to go down, that means the lights go out or power has to come from somewhere else. So we developed this contoured cutback tool that allows the technicians to make a precise cut exactly where they need to. So this entire contoured cutback tool has been 3D printed. The only off-the-shelf components we had to use were some screws and the actual pneumatic spindle. We were printing this tool as a prototype, but we found that the Markforged carbon fiber composite material is actually robust enough to withstand field use. So we developed 4 kits that are deployed locally.
The Markforged printers have allowed our engineers to be more innovative by encouraging them to fail fast. It allows them to print multiple different designs, make changes to them without having to do that in a design space. And it allows them to get to a final solution quicker, to respond to these rapid prototypes that we have to develop for our business. With the additive manufacturing and the industrial Markforged printers that we're using, the sky's the limit.
All right, so that was the final customer example. So let's wrap up a few of the key Markforged points and advantages that we've went over here today. So the first and most obvious one is that you're able to cut lead times, and this can be both in the manufacturing and the prototyping phases as well. So in the example of prototyping, if you ever need to make a small change to a part, like a different size fillet or something like that, and test that change, you can send the updated version to your printer and have the new file ready to actually test within the span of a few days. This obviously applies to manufacturing too. And if you're making an end-use part, you can just cut out sending a part to a machine shop or waiting for parts to be shipped back to you because they're just being made in-house, right? And so the next one is that because you're able to produce items quickly, you don't need to keep an inventory of dozens of jigs or fixtures because you can just print them when you need them. Basically, this makes all your inventory digital and lets you save space if that's premium to you. And then lastly, you can save a lot of man hours for your high skill staff. So if you have machinists in house that can create all these parts that we've been talking about, they probably have queues, and they still need to work through those. And those queues might have parts that are just more important than others. So even if you still could run, even then you still could run into delays of just getting the part in your hand if they're making everything. So again, the printers here are unmanned and they don't need highly technical staff to operate. So you can let your high skill people focus on the things that need their attention rather than, say, just to bring up a previous example, machining something to hold the important item that actually needs a critical machining operation. I think this goes back to what I was mentioning earlier in this presentation, that there's a lot of manufacturing methods and Markforged isn't going to replace CNC, but it's another tool in your toolbox that can do some things better and free up limited times for other things. And so that's all I had today for you guys. I want to thank everyone for sticking with us here today. I want to say thanks again for everyone's time, and I hope everyone has a good rest of your day.